which one? So you my Excel of this is you should my profile. We are going to use it all hopefully keep Semantics. Yeah, okay. I input my component to the link of the secretary. We are in two. Volunteer, so in two. Yeah, typical we are in two in order to avoid. Yeah. Webcam? Then? Webcam? Oh, no. There is no, we should use the external one. No. I have to ask for one webcam. So we test before we download first the presentation. Yes. And then they can try if they want. Asian trinkets. Okay. 5. Okay. Yeah. Okay. We have to. Share and screen. Okay. On the Zoom. The second screen. Okay, let me just check if it's it's like you just look which ones. You go to the cover of the web account.
Okay.
Yes.
You can just use the window webcam. It's also fine. Oh, no offense.
Okay. We can use these. We'll go to see.
Okay. Works. Do you want to try if your presentation is okay? Use like the presentation mode to check only the and read mode used to be English up to the phone. This is great. This. Yes. Here, just okay, thank you. Sorry, this one. This one. Maybe a bit more here. Here. Yes, there's the yes, okay. That's right. It's okay. Okay. Check this. Okay, which one is yours? SheetAgent. SheetAgent. Okay. Here should be the read mode. Here, just the slides. Okay, it's fine. Yeah, okay. Fine. Yes. here like in this folder. Okay. Yeah. Do you want to try? It should be good. Yeah. So we are going to start, and this is the last session of semantics. Today we have 5 speakers. The first one is Yufeng. He's going to explain us mixture of threads on private model parameters for personalized and federated one.
Hello everyone, I'm Yufeng. I'm honored to have this opportunity to share our work. Our title is PM-MOE. Now I will show some details. For the background for it, the digital economy is developing prosperous year by year. About 2025, a nearly center market size, nearly $35 billion US dollars. So the core of AI is data. It's empowering the financial, medical, government affairs, and communications. So this operator span that the data have the characteristics like distributed production and privacy protection. Recently, they have some data breach instance about past year. Change healthcare leaked about 6 TB of data, affecting more than 100 million people. And this year, the Webster Bank also suffered a data breach. So the more centralized data is collected, the greater the risk of the leakage. Now, the data cannot leave the class or domain, so the federated learning is a distributed machine learning. Methods can the data is stored locally and the model parameter are created to generate a global model. However, it is also serve the heterogeneous edge data across many clans. You will find each client have the different labels, different data features or different symbol size. So it motivates to the second topic, the personalized federated learning. Also, recently, studies indicate that there have model inversion attacks. Its user record gradients can reconstruct the original image from the image domain. So the next step is model split-based personalized federated learning. It split the model into parts. One is global aggregated to the server, and another one is local private parameters. And now, what should we do for that? Talk about our motivation. We test 3 experiments for that. One, we collect all the client data and to the one server and to train a simple model. You can see the performance is excellent. And the second, when the data move into the decentralized part, the client A local model you can see the performance dropped significantly. So the third experiment, we add the client B model, private model to add to client A. You can see the performance can be improved. So this means every client's private model can be benefited to other client. So we need to think about 2 questions: how to effectively use a personalized module, and the second is how to handle noise module parameters introduced by personalized module. You can see the picture B. The global model can reach the right target, and the client A private model and the client B private model can have the aligned results. It's very close to the target. When we add the client C, is far away from the target. So we need to solve these 2 challenges. We propose the PM-MOE architecture. It contains 2 steps. One is the pre-training step. Each client have the personalized module and the global module. The global module will upload this parameter to the server, and we will at the end of the step we will get the converged global and personalized module parameters. And in the second step, the PM-MOE step, the server will collect the global module and every client's personalized module without gradients. And then the server distributes the pool to each client. For one client, we can see we employ a gate to integrate every personalized module, and then we use the Helmholtz free energy to denoise it, to remove irrelevant private module, and reserved client model will be assigned the weights with the gates, and then together with the global module to have the prediction results. To the core innovation of that is a mixture of the personalized modules. It have 2 types of it. One is the personalized experts. Second is personalized parameters. The personalized experts can process data convert into the high dimension space vectors, and the personalized parameter cannot. And just touch dot double n dot parameters. The second innovation is in energy-based personalized model denoising. First, we need to set the energy formulation. We use constant similarity for energy settings, and then we compute the confidence for that. To the Helmholtz free energy, there has a solution that the lower energy indicates the higher similarity. So we use it to recognize the different data features distribution from each other. And then the experts are sorted by the descending confidence scores with the top gamma. For our experiments, we use 6 open data sets and with 2 heterogeneous data setting. When S equals to 20% class uniform distributed across M clans, and others is directlet width. When S equal to 0, it means 100% heterogeneity for the data setting. For the benchmark models, we really appreciate the personalized federated learning library from John. It's a PFL-lib. It contains many personalized federated learning algorithm for about the basic and share features extractor, share classification experts, and the personalized parameters like DBE. For the metrics, we use the evaluation of the global accuracy for this. It's a normal evaluation method. Our main results for that, the PM-MOE achieves optimal accuracy in 2 data heterogeneous scenarios. Theoretically, MPE accuracy improves gate networking nearly approach 100% when alpha about 0 and M is sufficiently large. The more information can see our paper for the full derivation. For the ablation results, PM-MOE integrates the directly enhance PFL performance, but will introduce some noise. So we use the denoising component to further amplify the gains. We have embedded the PM-MOE architecture in 9 sort algorithm achieve the optimal accuracy across 6 data sets under 2 heterogeneous setting. And then for the other experiments, we need to talk about how to design the parameters of the gating network. For the layers, the greater gating network complexity leads to the higher performance. The activation, we use the lake rules and nonlinear negative regions can enable to complex data modeling for effective parameter rating. And the initialization, we use the orthogonal initializations can have the best performance for it because each class have the private model from each other. The data features distribution is a large different from each other. So the orthogonal initialization can be best have a better performance for that. For the others experiments for this like top K learning rate or epochs, strong heterogeneity will have the higher noise. So we set K as the number of the clans nearly about the upper quartiles. And the learning rate MOE gating requires a higher learning rate than the pre-training models. For the iteration, because of few parameters for gating network, so higher epochs will face risking overfitting. So I say the other external some experiments. Okay, thank you for watching. Here are some QR code about the paper code and some WeChat. I appreciate your listening. Thank you.
So, any questions?
Thanks for your talk and amazing works. And actually, I think that you integrate the MOE to federated learning is to like trying to denoise some bad parameters uploaded by some bad quality clients. And actually, we knew that for many MOE, like many gates, actually,
Yeah.
we can activate multiples of experts at the same time. So is there any approach that we can, like, if we want to infer for an example in Cypher 10, if we want to infer an label like cat, and we can only activate the clients with a very high quality training data in cat, further enhance the MOE.
Okay, that's a good question. If the different labels can have, we will find the same task. It means if 5 clients have the cache labels, for 1 client we will choose 4 of them. But other clients doesn't have the cache labels, we will use a gate to denoise for it. It will compute between the data distribution to recognize which private model can be selected by the gating. Yeah. Yeah. Okay. Thank you. Okay.
So that
Thanks.
okay.
Okay.
So the next part is beyond dataset for the marking model level copyright protection. Model level copyright protection for code summarization models. The PowerPoint is only the slides are there.
Which? This one. Yeah, too much.
Hello, everyone. My name is Dee, and it's my pleasure to present our work in the WWDC conference in Sydney. And our idea is not that tough and not that hard, so I will make it quick. So this work is beyond the dataset watermarking. So normally we do the watermarkings on the data level. So we are aiming to using the model level watermarkings to protect the AI models. In this work, we particularly focus on the code summarization models. So give some basic ideas. So the code summarization models also we can say it as a code abstraction model. Is kind of it converts the code into natural languages to explain what's the purpose of or something like the right comments of the codes automatically. Okay, so it can improve the software development efficiency, accelerates the document generation, also enhance code maintainability, something like copilot things. We enhance and accelerate the software engineers to help them to write the code efficiently. So, but and also the training the code summarization models also is costing. Okay, we need still thinking about we need the GPUs, and we also need lots of times electricity bills to make a good code summarization model. So then we were arising a question. So if you cost a lot of money to train good models, no one wants to be like hacked or being sifted or models by other people, right? So we think about the problems of the unauthorized use of the CSMs or illegal use of the CSMs, and some people also we have secondary development or sales for the profit after the sift, right? So like when you have open source models and other business using your models to earn money, which is illegal. and also the illegal copies and the abuse and the damage models, something like that. This is the basic motivation. We want to protect the code summarizing models. So design an efficient and a practical model of intellectual property protection technology is become urgent now. It's not just like the code summarization models, we also for the other like vision models and also large language models. The existing protection technologies published on previous WWW and also FSE. So they randomly insert for the first work called the code protector. So the randomly insertion of the code samples at the alteration positions by predefined fixed keywords like trigger features. Okay, and still the basic idea of the watermarking is using backdoor. We in our group we always thinking we did a lot of attack and defense methods in AI models, but we always thinking if we can using the attack to do some benign things. That's the basic things idea about this as well. So previously the works using the data level backdoors, they make the words like triggers and make it as the watermarks, something like you can see the examples. We have original code and they watermarked by the code mark. So they just change the representation of the code and as it make it as a trigger. And also the C shows the watermarked by the code protector. And the table shows the code mark SPT translation examples. So this is how they using the data level backdoors to do the watermarking protection. And also this is the performance compared with them. And we found the problem of that. Firstly, both of them are not universal. They only can work with some of the codes. They can't used for every codes, very types of codes. For example, the code mark, so they are not perform type 2 watermarks. It's not perform well with the PHP. And also the type 1 is not work well with the Go and Java. So this is the problem. And their lack of steerance. Okay, if the watermarks being embedded into the code, if it easily be detected, your watermarks will be useless. So enhance the steerance is also an important task in this work. And then to initialize the watermarking with the model level, so we need to treat the code like a natural language. So we need to tokenize the code into as a natural language processing. We need to tokenize the codes. So this is the basic steps. So we do the word segmenter, which plays in key role in generating input and output of the model. And we break the original code or text into token sequences, such as we give the different token IDs to sequence all the tokens. The examples like here. So the images at the bottom is some examples we demonstrate the necessity of conducting the identify obfuscation and impact analysis. So the top images is about the verification method of our method MDMark, and demonstrate that the model inputs carrying the triggers can produce the predefined result. So the expected is even we have the wrong code, when the expected with the watermarking, we still have the correct output. But if the triggers being triggered, the output will be the different. This is the basic framework of our method. So the model mark method consists of 3 steps. The first, we have the identify obfuscation, which means we randomly select a code snippet and convert it into the abstract syntax tree, AST. And it iteratively replace identifies with a placeholder character unknown to generate a multiple code variants. So in the step 2, the impact analyze, we input the original code and its variants into the model and calculate the confidence score for each variant. And identify the identify in the lowest scoring variant, because this one we don't want we want to keep the high students. We don't want the detection methods detect the watermarks. So in the third step, the token substitution, and we're starting from the key points, identify the second step, and randomly we select 1,500 pieces of the data from the corresponding language dataset, and calculate the token frequencies and select the low frequency tokens for noisy addition operations to generate the trigger tokens. And finally, we will input the trigger tokens into the tokenizer to obtain the required merging rules, and fine-tune the tokenizer to embedding the watermarks. So this is the basic framework. And the experiment settings for the watermark, the code markers, and the code protector, for comparison purposes, we're using the original settings in the original paper. So this is the basic rules for also code mark. And for code protector, there are protection and poisoning as triggers, and the watermark as the watermarks. So here is the performance and experimental results we compare. In the first table is we compare the harmlessness of the watermark. So we don't want the watermarks to affect the model performance. This is the first table. And for the watermark validity demonstration, our method can show 100% result compared with the previous work. And also for the force touch without trigger and demonstration of robustness of the watermarks, we also perfectly surpass the previous works. And the summary of our work. So our feasibility can be migrated to the visual language pre-trained models as well, and the text branching of multimodal models. So the watermark embedding with the tokenizer suitable for text-driven multimodal tasks. So trigger tag design and combine the task with task-related vocabulary and reduce the performance impact. So with limitations, so for the watermarking is limited to the text modality, and image or audio modality needs additional watermarking technologies. It's not for the pure model level watermarking is not enough to do that. Also for the computer vision models, we also can extend our watermarking idea into that kind of models. But it requires continuous input and makes the watermark embedding complex. So this is another limitations to expand our work into other modality models. But this is also our future work. We are still investigating it. Thank you for listening. And any questions?
Any questions? I have one.
Yeah.
Because all the languages that you are comparing between all of them, there is no C, there is no C++.
Oh yeah,
There
because
is any reason for that?
first one is the dataset, and the second one is we're choosing the current most popular languages, especially the Python for AI, and then the Ruby and the PHP and JavaScript, which is most using for the web development, especially, and for the JavaScript and the PHP and the Go and the Ruby is because we are targeting triple W.
Okay.
So this is the.
I had that question because in C++ you are in a low programming language.
Yes.
So probably with the watermarking, the performance can change, no?
Yeah, I think you are right, because the language we are using the high level, but for the low level we will test it.
Okay.
Thank you for the suggestion.
Thank you. Questions? More questions?
Thank you. I'm a little curious. So basically, I imagine that if you want a watermark, it's like you want to show the source, right? Which company built this code. So I don't
So I just wonder in your work, so how to like distinguish different method to show the company, like you may have 10 companies and use your method. So which one is produce this watermark?
Yeah, this one, the watermarking is to protect the copyrights. This is to reveal the copyrights belongs to which company is about in after the lawsuit. But now you need to hide secretly collect the evidence first, then to defend your copyrights. This is the first purpose. We need to have something people will not reveal they're being identified. So this is the purpose of the watermarking, right? And after you say, okay, then we will know who owns the code when they receive the letters from lawyer.
Okay, so let's thank the speaker again.
Yeah, thank you.
And the next talk is SheetAgent towards a generalist agent for spreadsheet reasoning and manipulation via large language models.
Test. Okay. Hello, everyone. My name is Yibing Chen, a master student from Tianjin University. Today, I am excited to present our paper titled SheetAgent towards a generalist agent for spreadsheet reasoning and manipulation via large language models. So in the real world, spreadsheets are widely used across various fields, including but not limited to scientific research, finance, and marketing. So people typically rely on spreadsheets for tasks such as numerical computation, data analysis, visualization, and data management. So as a result, the ability to automate spreadsheet tasks is both highly important and in great demand. However, handling these tasks often requires a significant amount of repetitive labor and consultation, which not only consumes time and energy, but also increase the likelihood of errors. So the most closely related work to SheetAgent is SheetCopilot. SheetCopilot is an LLM-driven agent framework designed to automate spreadsheet operations by generating predefined natural language interfaces for interaction. And it also provides a benchmark for spreadsheet manipulation tasks. However, SheetCopilot has several notable weaknesses. The first is its predefined function calls generated by the LLM show poor scalability and are prone to errors. And the second, the LLM struggles with understanding spreadsheet data content, making it difficult to meet the operational demands of real-world scenarios. And the last, the overall design of SheetCopilot is relatively simplistic, lacking sophisticated mechanisms around the LLM, which leads to a high error rate. And let's illustrate the limitations of SheetCopilot with a simple case that involves reasoning. Given the champion sheet shown here, the task is highlight the competitions held in the United States in red, and SheetCopilot correctly identified the task instruction and decomposed it into the multiple execution steps. However, in the first step, it used the filter rule America, whereas the correct value in the table was USA, resulting in a failure to complete the task correctly. Based on this, we raised the following question. Can we build a versatile LLM agent that is capable of handling complex spreadsheet manipulation tasks involving challenging reasoning factors? A straightforward idea might be to feed all the spreadsheet data directly into the LLMs, but in real-world scenarios, this approach is truly impractical. So there are several challenges in using LLMs to solve the issues mentioned. The first, Spreadsheet data is dynamic. A complex task often involves multiple operations on the spreadsheet, leading to continuous changes in its content. So in such cases, sending the entire updated spreadsheet data to the LLM after each operation is actually impractical. It easily exceeds token limits and increase the risk of hallucinations. Second, most LLMs are primarily trained on natural language corpora, which limits their ability to understand semi-structured spreadsheet data. And finally, to build such a truly versatile agent, we also lack a realistic and complex benchmark that can effectively evaluate an agent's reasoning and manipulation abilities over spreadsheets. So to bridge the gap in available datasets, we have constructed a new benchmark, which is called SheetRM. This benchmark is characterized by the following features. The first, comprehensive categorization. We conduct a detailed classification of spreadsheet operations comprising 5 major categories and 36 subcategories. The second is longer task sequences. In order to assess the agent's instructing following capabilities, each task within the benchmark consists of multiple subtasks, and each involves distinct spreadsheet manipulations. The third is the reasoning dependent operations. Several subtasks are intentionally designed to incorporate reasoning challenges, including the complex computational logics, vague requirements, incoherent data format, and information extraction. And finally is the process level evaluation. We introduce an automated evaluation pipeline capable of not only determining the overall task completion, but also assessing the correctness of individual subtasks. And this is useful when we want to collect some high quality trajectories for fine-tune the LLM. The construction process of SheetRM can be broadly divided into the steps shown on the left. We initially crawl some spreadsheets from the internet, and we use GPT to generate some subtasks, which is like a draft, and we will manually filter the generated subtasks using the programming methods and the software-specific methods. We use this cross-validation method to filter the high-quality subtask. And finally, we will assemble these tasks according to its difficulty and the length of sequences. And we finally make the 317 tasks. So here are the 4 types of reasoning challenges mentioned earlier, and we provide detailed explanations for each category in our paper. So, and this prints the complete prompt we used to generate subtasks using GPT-4, and further implementation details can be found in our paper. And to quantitatively assess the challenges introduced by SheetRM, we propose an LLM-based framework named SheetAgent. And the SheetAgent is composed of 3 main modules: the planner, informer, and the retriever. So the planner is responsible for task planning and execution following a React-style framework. So at timestamp T, it receives the task instruction I, system prompt P, and the table description D, current spreadsheet state ST, and its historical planning information H.
So planner outputs an action A, which includes both salts and the Python code. So the code primarily utilizes functions from the OpenPy Excel library and is executed in a sandbox to obtain the feedback O. If code execution fails, the error information is returned to the planner to trigger replanning. And if successful, the process proceeds to the next step with new spreadsheet state and historical information. So the informer module takes the sequence of actions generated by the planner and asks the LLM to generate the circle queries, which are then executed to obtain a spreadsheet subview E. The subview is then fed back to the planner to facilitate deeper reasoning over the spreadsheet, helping to address reasoning challenges. And to enhance the robustness and the reliability of the planner's code generation, we introduced the retriever module. We collect high-quality spreadsheet manipulation code snippets from platforms such as GitHub and store them in a vector database. So when the planner produces error code, the retriever is triggered to search for the top key most similar code snippets, which are then used to augment the replanning process. And returning to the previous example, we can observe that SheetAgent, by accurately identifying the task intent and leveraging information enhancement through the informer, and yet successfully complete this task. And we designed our experiments primarily to investigate the following 4 research questions. And to this end, we selected 3 categories of benchmarks: spreadsheet manipulation, table reasoning, and the combination. For comparison, we include several baselines, including SheetCopilot, Data, and StarGPT. First, we address question 1. Table 2 presents the results of different methods on SheetCopilot benchmark and our SheetRM benchmark. So using GPT 3.5, we observe that SheetAgent achieves a 16.8% higher pass at 1 compared to SheetCopilot. And even without informer and retriever modules, SheetAgent still outperforms all other methods across all metrics, indicating that the Python-based code execution is inherently more reliable than VBA or such language APIs. So the table 3 presents the results on the typical table reasoning benchmarks, and the results shows that our SheetAgent has superior reasoning capabilities over the tables. So next we examine the question 2. In addition to the experiments with GPT, we evaluated SheetAgent on SheetRM using Queen, Llama 3, and Cloud as backbones. Even with smaller LLMs, we observed consistent improvements. In contrast, SheetCopilot struggles to complete 4 tasks with smaller models and achieves lower exit at 1 scores, indicating greater difficulty in generating viable solutions. And these results confirm the universality of our SheetAgent across a range of LLMs. And we then address RQ3. We explore the difficulty of SheetRM from 3 perspectives: task length, task category, and the reasoning challenges. And we categorize task length into short, medium, and long. And these 2 pictures show the result, and we can refer to our paper for the details. And finally, we did some ablation studies to answer the question 4, and we can see that each of our core modules in SheetAgent has greater importance, and they cooperate together to SheetAgent and get the best result. So, and our paper presents additional experimental results, such as vision enabled SheetAgent, cost analysis, and error analysis. And we refer to detailed discussion in our paper. We hope that SheetAgent and SheetRM can serve as valuable resource to the community. And thanks for your attention. Yeah.
Any questions?
Yeah, nice work. The data set is definitely, it is useful for the community, but looking at some of the approaches that you used, I mean, they seem to be a bit outdated. For example, the models that you use for WikiTQ. So I'm looking at like data. Data is like, right now I'm looking at the leaderboard. It is ranked number 10. So there are like stronger models out there. So why didn't you use some of those stronger models?
Okay, that's a good question. Actually, this work is a bit earlier. So
Yeah, so some of these approaches I see here, like 2024. I mean, so like at least data is ranked number 10. There are other approaches. 2024, 2023, they have higher rank. I mean, that they are stronger models. That's my point.
so sorry, I didn't get it.
If I'm looking at the leaderboard
Oh.
for one of these data sets, that WTQ that we have posted there. What I'm saying is that there are stronger models out there on the leaderboard, and it would have been fair to use some of those models.
You mean that data
Data is outdated. It is outdated.
yes.
The model is not as strong.
Okay, I get it. And when we do the experiments, data is actually data and binder actually is a better model in the stage, and the StructGPT, when we do the experiments, the StructGPT is the SOTA in some table readiness tasks such as tab fact and theta QA, and we compare our SheetAgent to these methods, and we will complete the experiments if you think these methods are too outdated. But when we do the experiments, they are actually the SOTA model. Yes.
One quick question, please.
Yeah, thank you for this interesting presentation. So do you mind if you can go back to the SheetAgent framework, that slide? Yeah, I have 2 questions on the method framework. So in the first block, I saw there is like a sheet state. So I'm wondering like, how did you define this state? And the second question is, there's also like, it seems like you also put the spreadsheet to the informer. Like, how did you do that? You just like put this whole spreadsheet to this informer, or you've used another method?
Okay, the first question is what makes the sheet state, and we can see these slides, and in the left, and there is a sheet state demonstration. Actually, we do not encode sheet state complex. We just enter the number of rows and columns, and each column name and its data type. And we don't want the LLM to see too much table content, because it may cause higher error rates and hallucinations, and because the LLM cannot very precisely understand the semi-structured table data. So this is my answer to question 1. And your question 2 is how the informer work. Is my understanding okay?
Yeah, like how the informer works, and with the input of the spreadsheet, it seems that like we put the whole spreadsheet into the informer.
So actually we input, we want informer to, we design informer to extract the key content in the entire spreadsheet, and this may not cause severe hallucinations to the planner, and it can improve the reasoning capabilities to the planner. So we import the several lines of the spreadsheet data into the informer, and we make the informer to we ask the LLM to generate the circle queries like in this slide, and the circle query is executed to generate a spreadsheet subview, and the subview is imported to the planner to generate Python code. Okay.
Okay, thanks.
Okay, let's thank the speaker again. Okay, and the next talk is MixedSAND, semantic annotation of mixed unit numeric data. Yeah.
I am Davut Rafi from University of Alberta, and what I'm presenting is the work of my student Amir Behrat, who couldn't be here. Okay. So what is the problem? The problem that we are studying is annotating tabular data. So imagine you are given a web table and you want to find out what the columns represent. For example, you know that this is a table about players. You have some quantities, for example, column 1, column 2. You want to detect that, for example, column 1 represents maybe the height of the player and column 2 represents the weight. So that is what you want to do. So when I'm saying that like annotating or detecting this type, really what it means is that mapping these to some properties in a knowledge graph. So that's the idea. Okay. We have lots of tabular data on the web, and a big portion of this kind of data is numeric data. So if we can annotate this data, this can help like many downstream tasks because often the data doesn't have annotation, or annotation is not reliable. You don't know how much you can trust this. I mean, if you can verify it, I mean, it can help, I mean, with downstream tasks. So this is the idea. The existing work, often they don't work with numeric data, or they make some simplifying assumptions that may not hold in real world. Okay. So some of the challenges with numeric data, one is that it changes over time. For example, my height, my weight, I mean, it's not static. I mean, as I measure it, it changes. Population of a country, those are the kind of things that change every day. Okay, so it's not that easy. I mean, it doesn't become static. Like it's not the like capital of Australia, which doesn't change that often. Okay, so that's one issue. Another issue is that knowledge graph may not have like, I mean, a good representation of, I mean, this kind of data. So, and, or it could be that the knowledge graph may have data in one unit, but basically I have my table in another unit or another scale. So those are some of the issues that basically make this challenging. Okay. And you may not know that given a column, you may not know whether there is a single unit or multiple units. So those are some of the issues that we have. Related work, we can break it down into maybe 2 lines of work. Some of the work that has been done on textual data. The first work, ColNet here, what it does is that it finds an embedding of the column that you want to map, and then it has embedding of your columns in your knowledge graph, and then it tries to find which one is the closest one. Okay, so this is one idea. Sato, which is another work, what it does is it tries to look at basically the context of a column, not only the column that you want to annotate, maybe look at these other columns and they can give you hints, like, I mean, how you can maybe annotate this column. Okay. And then there is also this SEMTAP challenge that has been running for the past few years. And this is like, I mean, where like people compete on like, again, annotating these tabular data. Okay, so these are on textual columns. Some of these approaches may be applicable to numerical column with kind of some limitations of their own. The work that is done on numeric data, one of them is you can do some kind of statistical testing. So what you have is that you have your column, you look at like your candidates in a knowledge graph, and then kind of do a statistical testing whether they are coming from the same distribution. I mean, something like KS test is something that is used in the literature. Another approach, which is, it does better than like statistical testing. This is a work that we did in 2023. Another student who did this. The idea was that you build a bipartite graph. So you have this column that you want to annotate, and then you have this candidate in the knowledge graph. So what you do is that you build a bipartite graph, and then you find a mapping. In this case, for example, I am mapping 2 to 1. The cost here is 1. And the goal is to find a mapping with the least cost. And that is the one that gives you the kind of the annotation. Okay, so it's kind of recognizes that the numbers may not match, but the closeness should be good enough. Okay. So the limitations, one is that some of those approaches on textual are done on textual column, may not be applicable to numerical data. And also these works make some simplifying assumptions. For example, all these works that I presented, they assume that the column has a single unit. I mean, that you cannot have like, I mean, 2 units, I mean, in the same column, okay? So what we are discussing here is that can we relax this assumption and how far we can go? The approach is simple. So what we do is that we try to basically it has 3 components: model generation. We try to break down a column into components or pieces that we think are basically single unit. So in a sense, you're given a column, break it down in it to a degree that you think like each component becomes a unit. Okay, and we are not sure, but at least we try. And then once you do that, instead of 1 column, you have now a set of columns. Annotate each one. So it kind of gives you a set of annotations, and then you do an aggregation later on. So to explain it a little bit for how we kind of like break down a column, one thing you can do is that maybe do clustering. An issue that we encountered when we use clustering is that something like simple absolute distance between these numbers, it often doesn't work. So for example, here we have this area, the area in kilometer square and meter square. And if you do that, you basically, you look at the absolute distance, this number here is closer to 684 than this one. So basically, if you're doing clustering, you're going to cluster this number with the one above, okay? So a solution that we found working in this case using something called Bray-Curtis distance. This is a distance function used in ecology when you have the distribution of species and you want to basically compare, or you want to find like, I mean, the difference, I mean, kind of, okay? So, and you can see that the distance becomes like a kind of relative distance. So there is, you take the absolute distance and then you kind of normalize it to somehow. It is still a metric. Once you use that, those two numbers on top form one cluster and these two form another cluster. So it addresses this problem. Okay. And then what we do is that once you you break down a column into pieces that you think are single unit, then you use like an existing method to annotate it. In this case, we use SAND, but you can also use other methods that just to annotate each one. And then each subcolumn becomes like, it gets a label. Okay. And one issue that we also had here is that the knowledge graph usually is not complete. It may have height in one unit, not other unit. We tried to expand the knowledge graph as much as we could using different conversions and so on. So that's another thing that we did. Okay. And then once you do the annotation, you have to aggregate it. The same issue that we had with distance when we were clustering, we had the same issue in the aggregation. So again, you have costs for different subcolumns. You cannot simply add those costs together because they may not be comparable. So again, this relative distance I just mentioned, this also works nicely with this aggregation. Okay. So one issue was that how you evaluate something like this. Well, we have some data set out there, web table data set, but we wanted to vary the complexity of the data set. So for that, we introduced what we call this MixedSAND data set, which allowed us to vary the difficulty. So for example, we have easy, medium, hard, and we could also make it even more diverse. Okay. So how we did that? For us, a data set that had units that were not separable, it was if the units in a column are not separable, that was a hard data set. You cannot easily separate, so you can do the annotation. But if the units can be easily separated, it becomes an easy data set. So if you look at this data set here, you can see that here we have weight in pound and weight in kilogram. If I reflect the weight from one dimension to another dimension, there is no overlap. This is an easy data set. And so again, here these red dots are reflections of those blue dots. And again, as we are doing is that the red and blue, they don't interfere. But if you look at this data set, if you do the same kind of reflection, what happens is that you can see that red and blue interfere. This is an example of a harder data set. The way we measure it, we use this concept of reflectivity. So for example, the reflectivity here is close to 1, which means this is a hard data set. The reflectivity here is close to 0, which means it's an easy data set. So this allows us to build this data set that vary in terms of difficulty. For evaluation, we use this MixedSAND data set that we created, and also WDC and metrics top in accuracy, unique unit detection accuracy, and we compared this to some baselines. SAND was one of them, and kernel density estimation was another one. Okay, so what KDE does, basically, it looks at this distribution, it tries to pick the picks, how many picks you have, and based on that, it figures out that, for example, here we have 2 peaks and there are 2 units in a sense. Okay, so it doesn't do the annotation, but it can detect maybe how many units you have. Okay, so on detecting whether your column is mixed or single unit, this is how MixedSAND is performing compared to KDE. So what MixedSAND is doing is that it's trying to it varies the number of clusters, and it finds the clustering that gives you the least cost. That's what MixedSAND is doing. Okay, whereas KDE is looking for the number of picks. So we are doing better than KDE here on these data sets. Here we are detecting the number of units, exact number of units that we have in a column. And here for our data set, it's varied from 2 to 5. And you can see that again, MixedSAND is doing pretty good, much better than KDE in this case. Okay. The next question was doing the actual annotation. So basically giving a column, mapping it to a knowledge graph property. So we have these easy, medium, hard data set. Here the state of the art that we could compare was our own early work, SAND, which was doing better. But SAND is for single unit column. It's not for mixed unit. But again, that's what we could do. So we compare it, and you can see that, well, MixedSAND is doing really well. Another thing that we did was that we said, well, what if you feed single unit columns to MixedSAND? I mean, so kind of, we know that SAND is, I mean, SAND, for single unit column, you use SAND. That is the model that you use. Okay, so what if you feed that single unit column to MixedSAND? How the model is going to perform? So we can see that it is pretty much comparable to SAND. So kind of we are not like, the performance is not much affected. So that's what I'm saying, okay? We have more results in the paper. For example, we show what is the impact of this distance, this relative distance we are using compared to absolute distance. How the model is robust as we vary the number of units. And also what happens when you vary the size of the query column and so on. So those are some of the more results that we have in the paper. Okay, to conclude, so we introduced this MixedSAND data set and a three-stage annotation pipeline to annotate mixed unit numeric columns. We showed the performance compared to some of the state-of-the-art solutions. Some future directions, we think the data set at least provides a challenge for the community to build better models. So and we are hoping that basically more models, people can build more models on this data set, and allows, I mean, kind of evaluate the progress. Okay. And running time, we didn't look at much running time. I mean, my areas in databases, usually we look at running time most of the time, but here focus was on accuracy, but improving the running time is another issue. And so with this, I will stop and I can answer questions.
Any questions?
Maybe if I couldn't get it, but like, how can you like achieve the like high reflectivity, like those like values are similar, like around 100, and then how could this using Bray-Curtis distance could achieve better results on like these kinds of things?
Sorry.
So
I have a bit difficulty understanding the question or hearing.
Yeah. So like you're using like the Bray-Curtis distance, right?
Yes.
And then how it affects how it improves to solve these kinds of problems?
How it improves the performance?
About these problems, these high reflective problems.
Okay, so we are using, yes, Bray-Curtis distance.
And then my knowledge graphs like help us to solve like these kinds of problems in these situations.
So which situation?
This situation.
Here?
Yeah.
Oh, okay. So this is, I mean, data set. I mean, kind of put that like, I mean, don't look at even Bray-Curtis distance or anything. This is just a data set. So basically, whatever method you have, how to evaluate it. This is an issue that we noticed that we didn't have, like, I mean, a good data set, a strong data set that we could evaluate. This is just, I mean, we are saying that creates a data set that we vary the level of difficulty so that we can evaluate. Okay, so this has nothing to do with Bray-Curtis distance.
So it's about like your data sets. Like
this is, I mean, this is the data set. So here what we have is that we have a data set. We are introducing a data set and also a pipeline. So this is just a data set. The data set that we can control how much like these units are separable or how much they are not. Okay. And the distance is like, I mean, yeah, you can use like absolute distance as well, but what I'm saying is that doesn't work because these units are not comparable.
So then like it's are separated, then how could like solve these kinds of problems?
How to
Like how to solve these kinds of like problems, like this example?
well, this is again, so what we want to do is that we wanted to kind of measure how much like overlap these units have.
Yeah.
And the way we did was that we used this concept of reflectivity. Reflectivity is a concept that was introduced in, I don't know, Web 2002, 2001 or something. This Rakesh Agrawal introduced it in a different context. We found it quite relevant. I mean, kind of what we were doing here is that basically look at the reflections of these points, and the reflection in this case, like these units, different units. So that kind of allows us like to nicely measure, like, I mean, that whether this is like, I mean, easy data set or complex data set.
Okay, I just thought of like other situations that like if there's like a price column and there's like like.
Oh, I see. So
like
you're saying that if you have multiple columns, yes, this metric, this measure extends to multiple dimensions as well. So you can look at like, I mean, pairwise, like, I mean, and then so it extends to multiple dimensions, and we discussed it a little bit in the paper. Yeah,
I got it.
But that's a good point. Yeah, thank you.
More questions? Okay, let's thank the speaker again. And the last talk is Omni-SILA towards Omni-sense driving visual sentiment identifying, locating, and attributing in videos.
Good morning, everyone. I'm the author of the paper from School of Computer Science and Technology at Suzhou University. I'm honored to present our research Omni-SILA towards Omni-scene driven visual sentiments identifying, locating, and attributing in videos at the web conference. So the presentation will cover our research motivations, our new task, our new approach, experimental results, and the contributions. First, the video contains rich emotional information. Accurately identifying, locating, and attributing visual sentiment is of great significance. Our research motivations focus on three key aspects. For the task, we aim to identify visual sentiment in videos, locate when it occurs, and attribute the reasons. For information, we consider both explicit things like facial expressions and implicit things like human actions, object relations, and visual backgrounds to evoke the scene's perception ability of video large language models. In terms of the approach, we leverage the mixture of expert architecture and coil intervention techniques to model and balance explicit and implicit scenes information. Let's move on to the new task we proposed. Here's an example. In a video, the result of visual sentiment identifying is negative fighting, showing a negative fighting emotion. The visual sentiment locating is from 8 seconds to 15 seconds, and the visual sentiment attributing is a strong man twists another man's arm and forces him to the ground, clearly explaining the cause of the sentiment. When constructing the new task, we made careful preparations. We choose TSL 300 and Kuva as the explicit and implicit dataset respectively. For visual sentiment attribution, we use GPT-4 to generate and summarize the attribution of each frame from 4 scenes artifacts, and then manually checked and adjust the inappropriate attributions. We also manually constructed the instructions for each video clip with the prompt, you will be presented with a video. After watching the video, please identify, locate, and attribute the explicit and implicit visual sentiment in the video. Next, I will introduce our new approach, SM approach. The overall framework consists of several key modules. So the first is things enriched modeling block. And in this block, we adopted different techniques for different things information. We first use MT-CNN to model explicit facial expressions, which can quickly and accurately detect facial expressions features in video. However, SHA-9 was employed to model implicit human actions, effectively capturing the details and the dynamics of human actions. Realtor was employed to model implicit visual object relations, precisely analyzing the associations between objects. We use the same tool to segment the visual backgrounds and combined with VIT to model implicit background, comprehensively processing visual background information. And the second module is the things balanced MOE block. We introduce things expert to model different things information. Taking advantages of each expert in specific things field, the balanced MOE was used to balance the contributions of different things to the task, ensuring that the information of each thing was reasonably utilized. The third module is implicit enhanced coil block. We introduce a coil intervention graph to model the coil relationships among the things information X, the fusion things feature M, the visual sentiment output Y, and the confounding factor C, helping us better understand and handle the complex relationships among these factors. The deconfounded coil attention was used to implement the front door adjustment strategy, highlighting the implicit things information beyond the explicit, making the model more sensitive to implicit emotional information. In terms of training optimization, we adopt two-stage training strategy. First, we use 4 manually constructed instruction data set to between video lava, enabling it to perceive Omni-scene information. The second stage is Omni-SILA tuning. Through the perception ability of scenes information, we further train the model to better handle the Omni-SILA task. Now let's look at our experimental results. In the visual sentiment identifying and locating experiment, we use the accuracy and F2 score to evaluate the performance of visual sentiment identifying, and MAP to evaluate the performance of visual sentiment locating. We also paid special attention to the false negative rates. The experimental results show that our SM approach performs well and has obvious advantages compared with other models. In the visual sentiment attributing experiment, we designed 4 metrics, namely semantic relevance, semantic consistency, sentiment accuracy, and attribution rationality to evaluate the accuracy and rationality of the generated sentiment attributions. We also use the GPT for automatic and human evaluations. The results show that our new SM approach also demonstrate good performance in sentiment attribution. We also conduct ablation studies to analyze the roles of the important components in the SM approach, removing the SPM module, the IC module, or things tuning lead to various degrees of performance degradation of the model, which fully proves the indispensability of these components in our method. Meanwhile, we studied the effectiveness of different things information and found that human actions and visual backgrounds are very important for recognizing both explicit and implicit visual sentiment. Visual expressions perform better on the explicit data set. Visual object relations show slightly inferior performance in both explicit and implicit visual sentiment, except in obvious and specific things. In the applicative study, the SM approach also shows good characteristics in attribution rationality. Finally, I'd like to summarize our research and contributions. First, we propose a new task enabling interactive visual sentiment identification, location, and attribution with video large language model. We proposed a new SM approach through the things balanced MOE module and the implicit enhanced coil module. It can effectively handle explicit and implicit things information. we manually constructed the explicit and the implicit Omni-SILA dataset, and the experiment fully verified the effectiveness of our SM approach. And thank you for your listening. I will welcome your questions and discussions. Thank you.
Oh, any questions? I have one question. I didn't understand well what is the difference between the implicit dataset and the explicit dataset.
Your question is about data set. It's about explicit and implicit data set, or explicit and implicit feature.
And what are your plans, your future steps in this field?
Okay, so first let's turn the page of our approach. So we define 4 experts to track down our new task. First in the area of sentiment, traditional method mainly focus on the explicit features such as the facial expressions, and mainly data set was all facial expressions data set mainly, and our paper focused on implicit features such as schema action, object relation, and visual background. Take an example as figure 1. The actions shows the man was fighting with another, so his action will help to track down our new task. And object relation shows and usually the negative sentiment was 2 objects. They have interactive, and if we extract the object relation information, it can help to track down our task. And moreover, the background information was often shows the sentiment. For example, a sunny day often shows the positive sentiment, and a rainy day or cloudy day often shows the negative sentiment. So if we extract these features, and will help to track down our task. And for the data set, for each encoder, we design a data set to pre-train our model to perception this feature. For example, the visual expression, we use a visual data set, and with the task, please describe the visual of this image is the explicit data set. And for implicit data set, we use action, object, and background data set to improve the perception of these features.
Okay, thank you. So let's thank the speaker again. I think it's time for a coffee break.
Yeah.